Hello and welcome to Teacherless. Today we're going to be working on redox reactions. And for good reason I said good luck, because I personally am not a teacher. I'm just a student for AP Chemistry. And this personally took me quite a while to understand, and even now I'm not completely sure that I do actually understand this in full. So, the equations that I'm going to show you, I am nearly sure that I got them correctly, but I would suggest searching for some other YouTube videos or actually just talking to your real teacher because I might have actually gotten this wrong. But hopefully I didn't, and hopefully this information is actually useful. So let's get started. A chunk of zinc metal is added to aqueous acidified potassium permanganate. Now, if you recall from our last video, when we were working on double replacement reactions, we had two different compounds. In this equation, we only have one compound. And to understand what's actually going to happen in this, we're going to need to know what happens when an oxidizing agent or a reducing agent is in a reaction. And the way to know this is to just memorize it. And there's a couple of charts you can find on Google, which is currently what I have pulled up next to me. And when you're first learning this, I'd suggest that you do use those charts, but you're going to have to eventually memorize them. So in our case, a free metal such as zinc is going to turn into its metal ion, and potassium permanganate is essentially MnO4, however, with the potassium. And that's going to form Mn plus 2 in an acidified solution such as this. So that's what we see right here. And if you noticed correctly, you should see that there is no potassium on the product side. And I wrote this for a reason, because this potassium is not going to actually matter in this equation. And that is because ion metals of group 1 are never reactive. And that's commonly Na and K, which are sodium and potassium. So essentially you can just write out the entire equation and just completely erase the potassium or sodium, or lithium, or some other group 1 metals that they have. Not they, the periodic table, but you know. So, now that we have this is not nearly balanced, and if you were to try and balance this right now without any knowledge, it would not work out nearly well. So what many chemists do is they split the equation into half equations. And these two are half equations right here. Now, if you look what we've done, we have the products over here, and we have the reactants over here. And this reactant, which is the reducing agent, becomes this reaction, or that product when it's in a reaction. And same thing for this and that. So essentially, what we just did is we split the two equations, because technically you can write it as two separate equations. And that's what we've done here. And from this, it's a lot easier to balance them separately. So, what we're going to do is we're going to add H2Os for every oxygen to balance it out. So over here, on the zinc, we don't need to add any H2Os, but here we would need to add 4. So that's what we're going to do right now. And that here is adding 4 H2Os. And we'll get to the electrons in a second. But as you can see here, now we have 4 hydrogens. And earlier we didn't have any hydrogens there. So we need to balance the hydrogens out. So in order to balance hydrogens out, we have to add hydrogens to the other side. And those are just free-floating positive ion charged hydrogens. So that's what we've done here. And so now we'll get to the electrons. So now that these two are balanced, which is the most important steps, first you have to balance out the oxygen, and then you balance out the the hydrogens based off of the water that we now inputted. That's now we have a full equation with some charges. And so if we ignore the electron right here, we'll see that we have 8 positive charges and 1 negative charge here. So that means we have a positive charge of 7 over here. And over here we have a positive charge of 2. So, clearly something is happening here, and that's that we're losing a negative charge of 5. So in order to display that visually, what we have to do is we have to add 5 electrons here, which then allows for negative charge to be produced. And similarly here, we're losing 2 electrons, which is why it becomes positive. And so that's what is being shown here, as the electrons are being separated from the zinc. Here, the electrons are being inputted into the magnesium, or manganese, sorry, which is why we don't see them. So what I've noticed as like a quick way to know where to put the electrons is that the oxidizing agent is going to have the electron on the left side in the reactants, and the reducing agent is going to have the electron on the right side. That's just like a quick way to memorize it. But now, what do we do to actually input these two equations together? Well, in order to do that, we need to have a balanced equation. And similarly to elements, electrons have to also be balanced. And if we were to try and input these together, we'd be destroying electrons essentially, because we'd have 5 electrons on one side and 2 electrons on the other side. And you can't destroy or create energy, so that can't be done. So in order, what we have to do is balance the entire equation by multiplying it by 2 or 5. And 2 or 5 is specifically for this example. So as you can see here, we'd multiply this by 5, so then we'd have 10 electrons here, and everything would have to be multiplied, so this too. And over here, we'd multiply by 2, so then we'd also have 10 electrons, and everything would also be multiplied by 2. So that's what we've done here. And I've also simplified the hydrogens. So if you check over here, the hydrogens were here, and there was some water over here. And in some other equations, there's going to be some extra hydrogens and etc. So if there were, we'd just like add them together. So that's why we got 16 hydrogens here, and 8 H2O here. That's from multiplying everything. And similarly, we have 5 zinc, 2 manganese, 2 manganese oxide, I believe that's what it's called, and 5 zinc. And this is the entire equation, actually. This is our fully drawn out equation. And before I go into basic equations, I need to mention one thing, which is that this equation here, I am 90% sure this is the actual correct equation. Now, if we go all the way back to the start of the equation, we see that it says aqueous potassium permanganate. Now, if you remember aqueous from our net ionic video, the issue with aqueous is that we'd have to remove spectator ions. And for the life of me, I could not find a single video that referred to that, besides a single document that did actually refer to removing spectator ions. So I just didn't remove spectator ions. And that seems to actually work perfectly fine, maybe just in this example, or maybe just in general, because if you do count out the charges, we should get, I believe, -8 on both sides. It seems as though 14, +14, sorry. If you add these all together, like the 2 manganese, so -2, 16, that's 14, and then over here we have 5, so that's 10 plus 2, that's also 12 plus 2, that's 14, or no, 10 plus 4, that's 14. So yeah, that does solve to be like logical, but sadly I cannot really like verify that this is the correct way to do it. But I'm like 90% sure. So you're just gonna have to take my word for that. So let's get on to basic equations. Like pumpkin spice lattes, and like Starbucks white girls, you know, whatever, basic. You can insert a couple of other very bad basic jokes, or like acid jokes, whatever. I really don't care. I'm way too tired for this. Alright. So, a solution of iron 2 nitrate is added to basic solution of hydrogen peroxide. So, I've taken the liberty of skipping a couple of parts for this, because it is essentially the same as the previous question. Obviously, we're going to have two separate things, like two different compounds mixing together. And so you're gonna have to check the chart for that. So iron 2 nitrate is an oxidizing agent, and hydrogen peroxide is a reducing agent. So when we write that out, we get this. Now, this obviously is not balanced, and there is a special thing that you have to do for basic, which is why I separated basic and acid equations. And the difference between them is that you have to add OH groups. And this, I haven't mentioned it yet, I believe. No, I have not. This is just to separate the half equations. So give you a second to look at that. Not necessarily anything to explain. It is the exact same as the previous equation. And this is the OH groups. Now, the reasoning behind adding OH groups, I do not know. That's just how chemistry works. But before you balance, after you balance out the oxygens and the hydrogens, you have to add OH groups based off of how many hydrogens you have. And you have to add the OH groups to both sides of the equation. Not just the hydrogen side, but both. So that means that we have 5 hydrogens here. That means 5 OH groups. And similarly, we have 5 over here. And we have 9 and 9, and also 9. And hopefully you'd recognize that 5 hydrogens plus the 5 OH groups, they would simplify into water, which is what we've done here. So we have 5 H2O, 5 OH, 9 H2O, and 9 OH. Now that we've done that, we can actually get to the electrons. So essentially, the OH group comes after the oxygen and the hydrogen, but not before the electron. No, but before the electron, sorry. So it'd be the third step out of a 4-step like process, essentially. So now that we've done that, we add the electrons. The electrons are the exact same process. I have not written out the negatives and the positives, but the OH groups are negative, and I believe the H2O2 over here is positive, and you should recognize that if you were to write that out yourself. So then, after combining all of them, multiplying the electrons, so 9, which means we're multiplying everything here by 9, and everything here by 5, that ends up being this full equation. And that is a very long equation with a lot of numbers, which is why I still would suggest that you look at a couple of other YouTube videos just to make sure that I am actually correct. Or if I'm completely wrong, don't listen to me at all, unsubscribe, do whatever you want. I don't really care. But, so yeah, this is the supposed equation. Similarly, this is also the supposed equation. And that's pretty much it. Yeah, subscribe. There's not that many things that I feel like are necessary to mention for this. I would say that if we go all the way back to understanding oxidizing agents and reducing agents, oxidizing agents are going to be reduced, and reducing agents are going to be oxidized, which means reducing agents are going to gain positives, or they're going to become positive, and oxidizing agents are going to become negative. And a good way that I thought of oxidizing is oxygen, and oxygen is very electronegative. So, essentially, what you can say with oxidizing agents is that the oxygen is taking the electrons, whether or not there's an oxygen, you can just say, like, whatever is taking the electrons from the compound. So, if we look over here, for example, the zinc is losing its electrons by the manganese oxide, or if this is manganese oxide. And then similarly, because the manganese oxide took the electrons, it is now negatively charged. And to understand why this is positive and that's negative is just a big process on understanding like the actual charge of this. And that's just like a separate video, or just like that's just like a separate thing to understand. So I'm not gonna go over that. But that's essentially everything. So yeah, have a good night.